Oh, the test is coming and Brett wants to know what equations do we need. Okay, so magnetism test is coming on its way on Friday, and here are all the equations that you might need for it. You need to know that if you have a charge moving in a B field with some velocity, it will have a force exerted on it. This is due to the right-hand rule. If you needed to justify something and it moved a certain direction due to this cross product, you could justify it by saying, I use the right-hand rule, and that's what a cross product does. We also know that if we have a current carrying wire, that current carrying wire along its length will cross to the B field that it's within, and it will feel a force. What does that do to? The right-hand rule. Okay, cool. So we had those. It's also important to remember that if you had a particle entering into a B field, and our B fields are uniform because we're, simple high school students. If I use my right-hand rule here, I'm going to get a circle out of this. And this is implying that F equals Q V cross B equals M V squared over R, because this is a centripetal force here, or rather, this is the centripetal force, and this is what gives it, and this is our centripetal force by the centripetal acceleration here that causes circular motion. Circular motion, circular. Okay, I don't know, that was weird. But that's one of the equations we need to know there. If you've got circular motion, that's what we're thinking about. Other equations that we have for this test. We know that if you have a infinity long wire with a current running through it, you can get a B field at some point away from the wire. This is like some radial distance. We know that B field by the right-hand rule is going to wrap like this, because your fingers make the B field. But that B field at that radial distance, whatever it is given to us by, we can either do this with Biot-Savart, or we could do this with Ampere's law. In the end, we get the same equation, mu naught times the current enclosed, which is just the current of the wire, divided by 2 pi r. If you have a curved loop, and it's a circularly curved loop, and this is some radial distance here, then you can get the B field at that point, given by the current running through this, by saying it's mu naught I phi, where phi is some angle given to us in radians, whatever this is. Maybe this is something like a total of pi over 3, I don't know. But whatever it is, it goes in there, divided by 4 pi r. Okay? You won't need this for the test, but if you have a semi-infinite wire, and this was briefly talked about in one of the derivations we did possibly for AP, C, if you have a semi-infinite wire, then the B field due to a semi-infinite wire is mu naught I over 4 pi r. Okay? It turns out when you have an infinite wire, you double everything, and that 4 becomes a 2, but you don't need that. It's just a thing. We talked about it briefly when we did the railgun problem in class. Okay, so those are the Biot-Savart / Ampere's laws. What else do you need to know? Well, you should know some information about solenoids. This is a solenoid. And you should know that if the solenoid has a current running through it, and let's say the current is running around like this, if we wrap our fingers in the direction of the current, our thumb points in the direction of the B field. So that is north. Remember, the B field outside of a solenoid is 0. On the inside of a solenoid, the B field is equal to mu naught I n, where that little n there is the turn density. Remember, little n here equals the number of turns per unit length. We were able to get this using Ampere's law, where we made an Amperian loop kind of like this, and 3 of these edges, 1, 2, 3, meant nothing, and the only thing we cared about was the center on the inside. what we were basically able to say out of that when we did that derivation, if you want to go back and watch it, but what you quickly get from B dot ds, which is equal to mu naught I, is you get B times L, and there's an N here because we went through many of these. So, oh no, there's an N here. There's an N here because you did it many, many times. Excuse me. So then when you simply just divide by L, you get little n back. So that's the B field inside of a solenoid. Outside it's 0. And the last thing you need to remember that we talked about for this class is if you have a toroid, which is like the donut, the loops of loops of loops of loops of loops, you know that the B field on the inside of a toroid is 0, on the outside of a toroid it's 0, and within the toroid, what's your B field? Your B field is given to you by, let's see if I can remember this, mu naught I, there's an R that goes right here. I know it's over R. Or is it? Yeah, it's over R. It's something over R. Is it N over R? Mu naught I N over R? Here, let's just go back and check it out. So if we go back to our toroid, where is it? Toroid derivation. It's mu naught I N over 2 pi R from whenever we did this derivation here. And that's because whenever you make your Amperian loop, you get your 2 pi R, and then mu naught I enclosed is I times some number of n, and then you get your 2 pi R in the denominator. So we're going to get mu naught I N over 2 pi R, and that's because this Amperian loop, whenever we run the closed loop integral of B dot ds, which equals mu naught I enclosed, so we multiply it by n, this ds is a 2 pi R, so we divide it, and we get this here. So this is the B field of a solenoid. Okay? That's it. Those are all the equations from top to bottom. Okay, so yeah, those are all the equations you need. Naturally, you should be able to graph stuff. You know, if you're looking at, you know, how do you graph this equation right here, right in this one I'm highlighting in blue. You know, this one is clearly a 1 over r. So if I'm graphing this, you know, what's the B field is radial position. It's going like that. It's going as a 1 over r function because mu naught I and 2 pi are all constants. The 1 over r is the only thing that's changing. You should know all of your right-hand rules. Oh, and you know what? I lied. That's not all the equations there. I lied. There's just a few more. The last thing we talked about was inductance. Inductance. Oh, I can't spell at the moment. It's been a long day. Inductance. There it is. Spelled it perfectly. You know for inductance that the EMF you're going to generate is equal to the opposite of the changing amount of magnetic flux in some amount of time. And you know this flux can be thought of as the B field dotted with an area vector, so that's BA cosine theta. So your B field could change, your area can change, or the cosine of theta can change, but remember, it's only what is within the field that matters. If you make your area larger than the B field itself, you're not gaining anything extra. This negative here is due to Lenz's law, which states that this EMF you're generating is opposite of the direction of the flow for the change in the flux. And from this, we were able to say that the EMF generated from a generator was equal to omega, or W, NBA, so the Women's National Basketball Association, times sine of omega t, and that's actually giving us alternating current, like that, where these peaks here are just the WNBA term, because the biggest number sine could ever be is equal to 1, which we just kind of remove it from the equation. And the very last thing that we learned was with transformers. Rhizobs in disguise. I don't know why I paused there so much. And for transformers, you learned that your voltage on the secondary over the voltage of the primary is equal to the number of turns on the primary over the number of turns on the secondary. So if you knew these three things, the primary voltage and then your turns, you could just multiply by the primary voltage to get your secondary voltage. We also learned that if you wanted to do this for currents, you could say that the current on the primary, or we'll do this for the secondary, the current of the secondary over the current of the primary is equal or proportional to, well, it's equal to because of the ratios, the number of turns on the secondary over the number of turns on the primary. So those are the last two things. Once again, if you wanted to find currents, you just multiply over. And that is it. That is everything for AP Physics 2 in terms of magnetism. Okay? So, sorry I forgot about those last things over there with inductors and transformers. We've been talking about inductance a lot with the AP Physics C content recently, so that's why I kind of forgot that briefly. But I am confident now that that is everything you need for this test. Bye.